Hello everyone, welcome back to Linked Frequency. In this tutorial, we are going to learn about AC to DC power supply design using EasyEDA. This is the fourth tutorial of practice projects for PCB designers. I am Vaibhav Sugandhi, passionate PCB designer and technology startup founder, here to help you to learn PCB designing by doing a lot of projects like this one. So let's get started with our black box analysis as usual. First thing first, in our black box analysis, we need to arrange the box which are necessary as per the functionality and feature of the project. In this project, we are assuming to generate a plus 5 volt DC from 230 volt AC coming from the outlet in India. First thing we need is an input connector which will take the 230 volt AC to our PCB. One important matter to be considered here. I am assuming we are using a transformer that is mounted on the PCB. In general cases or in the most cases, industrial applications uses the panel mount transformers, which are mounted on the panel or the casing of the entire product. However, in our case, we are using a transformer that is mounted on the PCB. Hence, we are using the input connector for 230 volt directly. Thereafter, transformer is selected in such a way that it will transform the 230 volt AC into a 12012 AC. In the bridge rectifier, the rectification process is used to convert the AC voltage into a pulsating DC voltage. The 4 diodes are connected in a bridge fashion, that's why it is so called a bridge rectifier. Thereafter, input filter capacitor is added after the bridge rectifier, which is responsible for removing the unwanted AC component in the pulsating DC voltage. This purified pure DC with a little bit of spikes and a variation will be supplied to the regulator, which is a 5 volt regulator at this point of time, which will be responsible for converting the unregulated DC voltage into a pure DC voltage. Though the regulator is added, there is a possibility that impulses and the thermal spikes are generated by this linear voltage regulator. Hence, we will be adding an output filter circuit which is responsible for converting which is responsible for removing the unwanted noise that is generated by the regulator. Thereafter, we will be having an output connector with a good rating of current rating 5 ampere or maybe a less than 5 ampere, but at least more than a 3 ampere connector, so that we can connect the output of this 5 volt regulator or the entire PCB for our any application. To indicate the output power assuming or available for the connection, we will be using an indicator, which is a red color LED in all cases. This is how the black box analysis looks like for the AC to DC converter circuit. Again, this is a practice project, that's why I kept it very simple and straight to the point. Now we will be doing a morphological chart for one component in the black box analysis. Again, we need to do a morphological chart for the transformer, bridge rectifier, capacitors, and also output connectors, input connectors, as well as for the indicator circuit. However, for sake of simplicity, I am doing a only morphological chart for 5 volt regulator IC. Here we have multiple options and multiple features to be compared, and this is exactly the same morphological chart that we discussed in our previous tutorial. Again, we will be filling all these information by referring the data sheet, and then we will be doing a screening and scoring methodology. By doing a screening and scoring methods, we will be identifying that LM7805 is the outstanding component among these 4 options. Hence, we are selecting a 7805 or LM7805 component for our 5 volt regulator circuit. With that particular component, like all the other morphological chart, we will be having all the components in our white box analysis. First one is a terminal block with a 5 ampere of a rating with a 230 volt AC capacity, and then we will be having a 12012 transformer with a 1 ampere of a current rating, so that we can achieve at least 850 or at least 900 milliampere of a current rating at the output side. However, if you are expecting at least 1 ampere, then make sure that you connect at least 1.5 ampere of a transformer. And then 2W10 is a bridge rectifier with a 1 ampere of a current rating. Accordingly, you have to increase the rectifier as well. And then 1000 microfarad 35 volt capacitor, a filter capacitor, and LM7805 regulator, linear voltage regulator. Then we have 100 microfarad 16 volt capacitor, a T block for a 5 ampere of a current rating at the output of 5 volt DC, and 5 red LED. This is our white box analysis. Here I would like to go with a little important calculation. The calculation is we need a 5 volt DC here. For that particular 5 volt DC, according to the datasheet of LM7805, we need to provide a 7 volt DC at the input at the minimum level. If you provide anything below 7 volt, then the regulator IC will not produce a 5 volt DC at the output side. That is called a linear voltage dropout, or the dropout voltage for the linear voltage regulator. And to achieve a 7 volt DC at the input side of the LM7805, we need to calculate the VAC, which is input AC voltage for the bridge rectifier. The 1.414 is the RMS voltage for the AC to DC transmission of the bridge rectifier. If I use this particular formula, then I will arrive at approximately 10 volt AC to be provided or should be provided at the input of the bridge rectifier, so that we can expect a 7 volt DC at the regulator. However, we are using a 12012 transformer, so which is greater than a 10 volt, then we need not to worry about this particular situation. But in case of a 12 volt rectification or 12 volt regulator, on that time you need to use at least a 18 volt transformer at the input side. To ensure a proper functionality of the entire circuit, you make sure that you use these formulas and calculate the minimum input AC voltage for the bridge rectifier. Accordingly, select the proper transformer. Now let's jump on to the Easy EDA tool and start with designing our schematic according to our white box analysis. So here we have a Easy EDA software and the 3 projects that we did in a previous tutorial. Now I'll go to the file, create a new project. Alright, so we are done with our schematic design now. We have seen that two capacitors are having a different footprint and the resistor has to be through hole. So I hope you have learned that particular selection process in our previous tutorials. Now the important thing is the transformer has to be found on the global library. It is not available on the local library, as well as the 2W10 bridge rectifier has to be selected properly from the global library as well. We can select any one of them by using a 2W10 part number reference, but I have selected the one which represents the actual symbolical representation with the diodes and all. If you select with the IC and all, also fine, there is no problem in that. Just to understand how exactly it looks like, I have selected the proper one. So those are the two components which you have to select from the global library. Other than that, everything else is available in the local library pretty much, and you can do the same circuit as you did in the 5-volt power supply design. So this is how the entire schematic looks like. Now let's jump onto the layout activity and we'll discuss the further points. All right, so this is how the PCB looks like for AC to DC power supply. This is a linear voltage regulator based power supply which will convert a 230 volt AC into a plus 5 volt DC. Of course, I'm assuming this small transformer here is the PCB mount 230 volt to 12012 linear transformer, step down transformer. Okay. So this is how the entire PCB looks like. This is how the track width and all the design looks like. Using this the top silk layer legend as a heat sink area and the product name and hashtag linked frequency and AC input and DC output plus 5 volt and a ground indicator. All this is very essential and very important. Once you start doing those things, that is where the professionalism looks like. Okay. And the designator alignment is also a fundamental one, and adding the mounting hole is also a fundamental one. I hope you have noticed in the process of designing this one, my board outline was not as expected as when I started the PCB designing. As per the completion of the step-by-step approach, I discovered that I have to adjust the board outline accordingly. That is how the PCB designing goes if the constraints are not given. If the customer is already given you the constraint that this is how the mounting hole should be and this is what the dimension of the PCB, then you cannot do anything. You have to follow the procedure and you have to use the same dimension given by the customer. In case of such project where there is no dimensional requirement or there is no constraint for the dimension, you can optimize it as much as possible from your side. So this is how the entire PCB designing looks like. Now we'll go to the 2D and 3D diagram. This is the 2D dimension or a two-dimensional view, and if I remove the grid lines and if I rotate it to the bottom side, this is how the PCB looks like. Of course, we can change it to the green color and we can visualize it. And if I go to the 3D section, then this is how the 3D section looks like. A transformer 3D model is not available and the connector 3D model is also not available. I don't know, last time we had seen those connector 3D model. This time it is not visible. Maybe some reason for that, technical reason. But this is how the entire PCB looks like. And heatsink is absolutely at the same place as mentioned in the IPC standard. So no need to worry about it actually. So this is how the 2D and 3D diagram of the PCB. And if I go to the file and if I click on the PCB fabrication file, check for the DRC, then there is no DRC error, then only it will generate this one. And if I want to save that particular Gerber file, then I can save it by giving an extension as .zip zip file. And then I'll go to this file and export to the PDF level. And if I want a full color validation document, then I'll go for the full graphic. If I want it for a toner transfer method, then of course it is better to go with black on white, and that is only the option. Uncheck all the options and keep only bottom layer and board outline, multi-layer and whole section. Click on export and save this one as a PCB underscore toner transfer method .pdf. And then we'll go back to the schematic again, and there we will be going back to the file, export option, PDF for a schematic export. If you want to export a BOM, then click on export BOM. This is how BOM looks like. If I click on the export option, then these are the options which I have to select. So I'll select a couple of them and I'll remove the price section. Why? Because it is not necessary. And then we will be having a naming section here, BOM AC to DC power supply .csv. Okay, this is how our BOM is saved, and this is finally the process of converting AC voltage into a DC voltage. I hope you have all understood exactly the process of converting AC voltage into a DC voltage by means of linear voltage regulator. This is how the schematic looks like, and PCB, and then 2D and 3D diagram. All the other files that we discussed are already shown to you in the previous tutorial, and they are stored on the location where you save them. So there is nothing much to discuss about them. I think now we got these connectors. Maybe an internet issue because of, it takes a lot of time for loading these models into a file because it is a rendering process, right? So, all right. Thank you so much, guys, for watching this video. I hope you enjoyed and I hope you learned new skills in designing the AC to DC power supply in Easy EDA. I hope you enjoyed the entire process. consider subscribing to our channel Linked Frequency. See you again in the next video. Until then, tune yourself to make a difference.